some tools, and yeah, I just want to go into some of the NVIDIA tools that are available there in a slightly more detail. Starting out with debugging, I guess the single most powerful debugging tool for GPUs is Printf. So Printf is Printf, one would think. It's not quite as simple, but you can assume that pretty much all of the basic features of Printf, all the basic formatting characters are understood. It requires a device of SM20, so a Fermi device or higher, or newer. You don't need to worry about that on 30. All you have to do is, oh, sorry, yes, I need my microphone. Yeah, so Printf is Printf. Not a whole lot of differences between the CPU side and the GPU side. However, there's a few things that you need to be aware of, and that can create some confusing situations. One is that Printf uses a fixed size buffer on the device. So depending on how much output you create and how often that you actually give it the opportunity to flush this buffer to screen or to the command line, you might run into the situation where some of the output is not showing up on screen. So it's a circular buffer, and just the more you produce, the more likely you will just overrun some of the output that you produced before. The other thing is that the buffer is only flushed every so often. Basically, if you have a kernel that uses Printf within the kernel, this output is going to sit on the device until you launch the next kernel, or until you have some synchronization calls. The exact list is in the programming guide, but it's basically if you have a CUDA device reset or a CUDA stream synchronize and a few more of those fairly heavyweight calls, that it then goes out and checks if there's a buffer, a Printf buffer available. It pulls it over to the CPU and displays it. So, yeah, one thing to that's just something to keep in mind when you're not seeing the output that you would expect. And that also means that, right, the output from the device comes completely out of sync with the output from the host side. Otherwise, it's just your good old Printf. Actually, just one more comment on the formatting characters. The actual formatting of the string happens on the host. So you have, that means that the formatting characters are the ones that are supported by your host compiler. Again, if you're all working under Linux and basically under GCC as the host compiler, it doesn't make a huge difference. Now there's CUDA-GDB. I'm personally not a GDB user, so I'm probably not in a great position to go into many details here. But basically, the way that you do it is you have to instrument your code first. Well, you have to compile it with debug symbols turned on. And you have to turn the debug symbols on for both the host and the GPU code. So that's why you need to provide the lowercase -g option for debug symbols for the CPU code, and the uppercase -g for debug symbol for the GPU code. In addition, you should provide the -gen code option. So basically telling the compiler to generate a binary for this particular architecture that you're working on. Because otherwise your code will go through the JIT compiler again, and it's unclear whether you will lose the source information, the debug symbol information, when you go through that step. So once you have created your binary, you run your application as you would, or you run GDB as you would otherwise. So it's CUDA GDB my application, just your binary. And then once you're on the GDB side, there's ways to determine your focus, right? GDB has this notion of a particular focus. That's one thread that you're attached to. And so there's certain state variables that you can query, like what device your current focus is on, which SM, which warp lane, and all the way down to an individual thread. And by specifying, for instance, and this will just print out what the current focus is, and by default it goes to thread 0 in block 0 in, well, thread 0 in warp 0 in block 0 on SM 0, so all at zeros. But by just providing thread, whatever, 42, thread 42 will allow you to put your focus now on one specific thread. And you can set your breakpoints. So you can go all the way to monitoring individual threads and walk through the application. Again, one of the reasons I'm not using GDB that often or at all is that in many cases, well, first of all, most of the kernels that I'm working on are actually fairly simple. And using Printf has served, in many cases, the purposes. Also, I personally find it very confusing to navigate with your focuses through an application. But that's, again, maybe just a question of getting used to it. Now, a tool that I think is very useful is CUDA MemCheck. And CUDA MemCheck is actually two tools. One is the memory checker, which is comparable to Valgrind, and the MemCheck tool within Valgrind. And then there's RaceCheck, which allows you to detect race conditions that you might have on, for instance, shared memory variables. First, for the CUDA MemCheck, one of the errors that you might find when you're writing CUDA code is that you're launching a kernel, and CUDA will report unspecified launch failure. And that's pretty close to a seg fault on the host code. So those are oftentimes fairly hard to find where exactly it happens. I mean, you know most likely somebody's writing out of bounds, or you're dereferencing a null pointer or whatnot, but yeah, what to do next? So all you need to do at that point is to rerun your application with CUDA MemCheck and then your binary. And CUDA MemCheck will show you the place where the problem occurred. Now, you don't really need recompilation. However, with recompilation, you can make CUDA MemCheck much more verbose. And so it might make it easier for you to pinpoint exactly where the problem occurs. In particular, there's the option, well, again, the -G for getting the debug symbol so that you actually have human-readable symbols. The other one is the line info that gives you some information about what line in your source that the problem occurred. And the R dynamic that gives you more information about which functions were called. So if you want to get a full backtrace or a full stack trace of your of the call sequence when exactly something happened, R dynamic will give you that information. The other thing is RaceCheck. So that's the second tool in the CUDA MemCheck suite. As I said, that one of the hard problems to detect sometimes is to determine when you have a race condition between a thread that's writing into shared memory and a thread that reads from shared memory. And in some cases, you have a certain ordering, and you think that the code works. But then under certain other circumstances, it suddenly doesn't work anymore because this ordering of when the read and the write happens relative to each other is different. And so, yeah, you don't know where to look for those problems. And the race checking tool can pinpoint to those locations. So it basically keeps track of which threads access what variable, and then if there's any situation where you have a potentially undefined state when they write and read from the same location. We have another example on using CUDA MemCheck that we can play with. So with CUDA MemCheck, CUDA GDB, and Printf, that probably serves whatever, 90% of the cases. There's other tools out there, DDT, for instance, as a more visual debugger. But yeah, debugging CUDA applications can be a bit tricky, but yeah, that's what it is. Yeah, Ole spent quite some time on trying that for a very simple kernel, but there was this very subtle erase condition that took a lot of time to isolate. So on the performance analysis, I mean, after all, GPUs are there to make code fast, so performance analysis is kind of a key feature. Kind of the easiest way to profile code, the oldest way to profile code with CUDA is the command line profiler. And you enable that one by simply exporting the CUDA profile environment variable. You set it to 1, and what will happen is that it collects information about all the kernel launches and will print this into a file for later inspection. Now, while the profile log is somewhat verbose and easy to read, it doesn't contain all the necessary information, and especially it's not in a form that can be used to then display some nice timelines of when exactly the kernel launches happened. So there's a few more environment variables that you might want to set when you want to use the command line profiler. The first one is to set the environment CSV, that's column separated values. So basically, instead of a verbose output, it will produce a just column separated value table in the output file of the individual events that it has been looking at. The other thing is if you have a parallel code, by default, the command line profiler just writes its file, the log file, into one single file that's whatever, CUDA_profile.log, I think. Now, if you have a parallel application and each one of your MPI ranks is profiling, well, they will all write into the same file and you get garbage. So one way to avoid that is to explicitly set the log file's name. And in this case, I called it profile underscore. And then with the %p, it will add the process ID to the name of the log file. And so you can create for all your MPI ranks individual profiling logs and then analyze that in a tool like the Visual Profiler. Also, by default, the profiler collects some information about the kernels, but there is much more information that can be traced. And so you might want to have your customized profile configuration file, and that's just a text file that contains some information of the data that you want to collect. And so, for instance, here we have a sample configuration file. That's individual lines, and that just gives you then individual columns of values that are being collected. The first one being the timestamp when the GPU started its work, when the kernel was launched. Oftentimes useful is the grid size, the block size, and so on. Here we collect information about the streams, And then, for instance, the number of active warps. How many warps were actually active per SM during the execution time? So that can help you to pinpoint performance inefficiencies. Now, a valid question is like, where the hell do I know these names from? And, excuse me. So one way is to just go to the website. So on the docs.nvidia.com website, there is the Profiler's User's Guide. Oh, I'm already there. And then there should be a section. So there is a section here that just tells you all the different options that can be collected. But there's actually much more data that can be collected from the hardware counters that you have on the GPU. And how to find the name of those, we'll get to in a second. Oops, no, not this one. This one here. So collecting this information actually on the XK6, on the old 30, that was the only way to produce profiles or even just timelines. Now there's a new tool, but unfortunately it's not the graphical one that you want to use on 30. But let me first introduce just the visual profiler, how it looks like and what you can do, especially when you have it sitting on your local workstation and you have the code actually running on the GPU in your workstation. So what you see here is just a screenshot of the visual profiler, and you basically get a timeline of the individual kernels and the memory transfers that you have between host and GPU. But in addition, it also gives you a whole range of analyses that it can perform for you. And so for this particular kernel, it has given us a range of pieces of information. Like it said that there is low compute utilization. The GPU is mainly idle. So that's a global view problem that has been identified. It's not an individual kernel problem. But then we also have a low compute to memcopy efficiency. So we spend a lot of time moving data between host and GPU and not a whole lot of compute there. And so on and so forth. So like that we don't have a lot of overlap and so on. So this gives you a first cut at what problems are out there, what could I look at, where can I start optimizing? Because in many cases, you're running your application, you see that the performance is what, only 90% of what you got on the CPU. So what can I do? Where is the problem? And so this helps you at least pinpoint some of the, give you some direction of where to start looking. And so this is from an example where we looked into doing a matrix transpose, and I can, if we have time, I can show you some more in detail what we looked at there. But so after let's go back one. So one of the things here was the low compute to memcopy efficiency, so that we needed a lot of data to be moved to the streaming multiprocessors for the amount of computation that we did. And so we could look into the kernel, and the kernel analysis then would tell us, again, a lot of information, like when exactly the kernel starts, ended, and so on. So all the information that we collected previously with the command line profiler can tell us how many registers we've used. But here is the cool one. It also tells us like how efficiently we load memory into the streaming multiprocessors, or how efficiently we write it. It has this beautiful exclamation mark telling us, hey, there is something wrong here. So while we have perfect load efficiency, so we load only as much data from the GPU memory to the streaming multiprocessors as we need, we only use about 1/8 of the data that we store, or we have to, yeah, we are not as efficient in storing data as we could be. We need to spend 8 times as much time to store data as we should. And as you can see, there's another few exclamation marks that could be addressed later on. But whenever you have a problem with a profile, looking into global memory accesses, that's usually a good starting point for optimization. And then the cool stuff continues. It's when you compile your code with -line info, the tool can actually pinpoint you. I think I have it highlighted a bit. The tool can tell us that we have an uncoalesced global memory access. And it says that we have too many store transactions, that they are non-coalesced. And it can pinpoint us to the line in the source where this happens, which line was responsible for this inefficiency. And again, apologies, I didn't go into the details of how to make sure that we do coalesced reads and writes, but just to recap, right? Coalesced reads means that all the threads within a warp are accessing adjacent memory locations. And that's what we do here, right? We have the matrix and we read them whatever, in column mature format. So yeah, we're just reading adjacent memory locations, perfect. But when you write out the transpose of it, we have huge gaps in between. And so that's why we then get the non-coalesced memory writes. And so as you can see here, the input data, my I is the let's see. I'm confused. That is most likely that's most likely already the optimized one. Oh no, the I is the index. Right. The I is the counting index. It's not the thread index. And so in this case, my index IN should be adjacent in memory. Yeah. So index. You can't read it, but you probably can see it on the slides. But index IN is basically adjacent thread indices access adjacent addresses, whereas index out is the Y index times the height. So you're multiplying the thread index by the width of the height of your matrix. So this is a mechanism that with NVVP that allows you to pinpoint the places of performance inefficiencies fairly accurately. And there's additional metrics. So for instance, one is branch divergence. As you remember, the threads are all executed in these warps. And so if threads take different control flow paths through the kernel, some of them will just sit idle, and others will perform some additional work. The overhead of executing these unnecessary instructions, where a thread basically just has to sit idle, that's counted as the branch divergence overhead. So if you have extra work that is being done simply because you take a different branch than your neighboring thread. So this is another one of those metrics that can be extracted from NVVP. And then finally, the occupancy. So the question of how many threads are running on the device relative to the number of threads that could be running on your device is here actually fairly high. I mean, we get 90%. So that's for kernels that are memory bandwidth limited, it's one of the key metrics to look out for. Now this is NVVP. Now one of the challenges with doing these high-level analyses as we have it in NVVP is that it needs to collect quite a bit of data from the kernel that is running. On the GPU, we only have a limited set of performance counters, and we cannot, in a single run, collect all the information that is necessary to make some of these high-level analyses or high-level metrics. So we have to execute the code several times. NVVP takes care of that for you under the hood, so the graphical interface does that. However, in a batch environment, as you have it on 30, that's unfortunately not yet possible. But CUDA version 5.5 is coming out eventually, so there is hope. But the key, or under the hood, NVVP, so the visual profiler, relies on a tool called NVProf, which is again a command line interface tool that allows you to collect all the same information, but you're not getting it, currently you're not getting it in this nicely digested form. So you don't see all the, like global load efficiency is some information that you have to clobber together from different counters. Now here just a few things we can see. So the way you use the way to use NVProf, it's basically just NVProf and then the name of the binary. If you do that, then you get some just some overall statistics about your application. So an aggregate statistics of your application. So if you call the same kernel multiple times, it will just tell you how often the kernel was called, what the average and the longest and shortest execution time was, and so on and so forth. With this extra option called print GPU trace, you will actually see for every single invocation of the code, and so in this case we called 3 times the transpose, you will get the same information. Well, the information per invocation. And so in this case, it was a bit boring because they took exactly the same time, all of them. But you can do quite a bit more fancy stuff with it. For instance, what we got here, what we looked at here. So you can monitor individual events, individual performance counters. And what we looked here is the number of blocks that were executed on each one of the streaming multiprocessors. Now, by default, NVProf just sums up the information for the entire GPU. So that's called the aggregate mode. But you can turn the aggregate mode off. And so you get, for each one of the streaming multiprocessors, you can see here how many blocks were executed on each one of those. And so, for instance, if you have a problem that has a likelihood of being highly non-load balanced, highly load in balanced, you would see it here that, for instance, one SM only executed 1 block, whereas all the other SMs executed a few more blocks. And so that's just one additional information that you can then take into into consideration when trying to optimize the kernel. But frankly, once you're at that level at looking into a kernel, then it's probably already working quite nicely. Now, as I said, both for the command line profiler and also for NVProf, it can be a bit tricky to find out what information can I actually collect. And so a helpful option for NVProf is the --Cray events flag that will just, for the attached GPU, tell you all the events that you can collect. And we will go through that in a second as well for 30. And yeah, here, well, I wouldn't have needed to go to the actual website, but in the documentation for the profiler, it tells us, for instance, what the global load efficiency, how that metric is computed. So in the NVVP, right, we had this nice GUI pop up and say we had a global store efficiency of 12%. Well, that meant that the global store efficiency was calculated as the ratio of the global store requested throughput and the global store throughput. Now, the global store requested throughput is, again, it's you can look it up in that list, what events that you need to collect in order to compute that. So it's a bit more painful right now as necessary, simply because we cannot collect for all the metrics that we want to have, we cannot collect all the information within one run. So you might want to run your application a few times to collect all the information, but you still can do it. If you have any questions along those lines, let me know, and I can try to help. But I guess bottom line here is that if you have access to NVVP and you are close enough to the machine that you can actually do a remote X connection with it, yeah, you want to use the graphical tool. And then another one is to actually instrument the code. Right, I've talked quite a bit about the different streams that you have, the streams of execution. Now there's a mechanism to insert so-called events, like small tags, into the stream of kernel launches. And you can put an event into a stream. We call it the start event, and you can put a stop event into it. And then there's a function to compute the elapsed time between two events. So that's a mechanism to compute, to measure the time that was spent inside or in a kernel within your application. It's not giving you any additional information than what you would get from the profiler. So usually this is no longer necessary. But I don't know, if you have an application that a typical one would be a graphical one where you need to display the number of frames per second that you display, right? And so in your application, you want to have to derive this metric. Then you want to do this in code. An important point here is that you want to add the event synchronize. That means you want to make sure that you're waiting for the stop to occur before you're actually computing the difference between the start and the end time. So this is it for the slides. So I would suggest we just look at some of the tools that we had discussed. So the first one is CUDA MemCheck, and for that I have sample5.cu. This is exactly the same as sample2, but what we've done is that instead of launching n threads, we're now launching 2 n threads. So we're launching way more threads than we have allocated buffer space. Right? In that example, we allocated a buffer of 100 elements, and we're going now for 200 threads. So we're accessing out of bounds. So we need to make that one. Oops. And so app run minus n1. Oh, let me make sure. Let me make sure that I have the CUDA toolkit. Module is loaded. So it's my app run minus n1 and CUDA MemCheck sample 5. Right, whoa, whoa, whoa. So as you can tell, MemCheck has worked as it should. And it will tell you here, right, so it gives us some information about right, that thread number, the 200th thread in blocks in the first block is trying to, is out of bounds, accessing its memory, and so on. So you can use this information just to pinpoint where the problem occurs. Okay. Now the other one that I mentioned is NVP Prof. And let's just use actually let's compile sample 3. And we, oh, yeah, sorry. There is, in order to use NVP Prof, there is a path to a library that needs to be set. And we can determine that by finding out where we have nvcc. And so we need this path, ld library path is, oops, is this one, oops, lib64 and ld library path. So, okay. So here we just use the basic invocation of NVP Prof. Oh, sorry. So we use the basic invocation of NVP Prof, no additional command line arguments. And so after the application has completed, we now see the kernel that was executed and the host to device and device to host transfers. Now, as I said, there's a wealth of options you can use, but print GPU trace. With this option, we should get a bit more information about the individual kernels. Right? In this particular case, it's a bit boring because we only launched the kernel once. So we see it down here. But we now also see when the mem copy occurs. We see the launch configuration. We see how many registers were used for this particular kernel. So quite a bit more information. And then if we want to collect more information about this particular kernel, we can do NVP Prof with the query events. And this gives us a huge list of, of all the events that can be collected. It's now breaking up here because of the font size. Let's see. But this tool allows you to go really deep about now I have a problem here, sorry. It allows you to go very deep into the individual parts of the architecture. Right? We look at things of, let's see, like how many cache hits we have, cache misses, like how many instructions were executed, instructions launched and issued. So there's, for instance, a problem that, we mentioned the effect of non-coalesced memory access, right? That if you have if each thread in a warp accesses completely different memory locations, it's basically serialized into multiple requests that go out to different chunks of memory. This is called a replay. Basically, you have one instruction that is being issued, but the processor executes this instruction multiple times in order to satisfy all the different address requests. And that can be very expensive, very time-consuming. And so you want to get a handle on that, well, depending on your problem, but it might be that you want to get a handle on how much replay overhead do I have. And for that, you want to monitor like the number of instruction issued versus the number of instruction executed. Right? The replay means that you're executing way more instructions than you're issuing. And so on. So there's just a huge list of signals that you can collect. And as I said, in the user's guide for the profiler, it will tell you how to convert these signals into metrics that give you some better understanding of your application. And now I'm definitely about to lose my voice. Yeah, so I think those are the main parts that I wanted to show here. Have I forgotten anything? No, so we looked at CUDA MemCheck. We looked into NVP Prof. I haven't shown you how to use the command line profiler, but again, that's just setting up the configuration file and setting the environment variable CUDA profile equals 1. And that's it. So I'm a bit early now. I would suggest, we continue to look into the samples, or if you have any questions, this would be a perfect time to start asking them. And or I'd also be very interested in just hearing about your applications or your challenges that you're facing. I know from some of you what they've looked at and what problems that they've encountered. If you guys have any particular concerns, or I'd be very interested in hearing about that. Okay, thanks very much. The thing is that the buffer is only flushed every so often. Basically, if you have a kernel that uses Printf within the kernel, this output is going to sit on the device until you launch the next kernel, or until you have some synchronization calls. The exact list is in the programming guide, but it's basically if you have a CUDA device reset or a CUDA stream synchronize and a few more of those fairly heavyweight calls, that it then goes out and checks if there's a buffer, a Printf buffer available. It pulls it over to the CPU and displays it. So, yeah, one thing to that's just something to keep in mind when you're not seeing the output that you would expect. And that also means that, right, the output from the device comes completely out of sync with the output from the host side. Otherwise, it's just your good old. Yeah, so Printf is Printf. Not a whole lot of differences between the CPU side and the GPU side. However, there's a few things that you need to be aware of, and that can create some confusing situations. One is that Printf uses a fixed size buffer on the device. So depending on how much output you create and how often that you actually give it the opportunity to flush this buffer to screen or to the command line, you might run into the situation where some of the output is not showing up on screen. So it's a circular buffer, and just the more you produce, the more likely you will just overrun some of the output that you've produced before. The other thing, provide the lowercase -g option for debug symbols for the for the CPU code, and the uppercase -g for debug symbol for the GPU code. In addition, you should provide the -gen code option. So basically telling the compiler to generate a binary for this particular architecture that you're working on. Because otherwise your code will go through the JIT compiler again, and it's unclear whether you will lose the source information, the debug symbol information, when you go through that step. So once you have created your binary, you run your application as you would, or you run GDB as you would otherwise. So it's CUDA GDB my application, just your binary. And then once you're on the GDB side, some tools, and yeah, I just want to go into some of the NVIDIA tools that are available there in a slightly more detail. Starting out with debugging, I guess the single most powerful debugging tool for GPUs is Printf. So Printf is Printf, one would think. It's not quite as simple, but you can assume that pretty much all of the basic features of Printf, all the basic formatting characters are understood. It requires a device of SM20, so a Fermi device or higher, or newer. You don't need to worry about that on 30. All you have to do is, oh, sorry, yes, I need my microphone. Printf. Actually, just one more comment on the formatting characters. The actual formatting of the string happens on the host. So you have, that means that the formatting characters are the ones that are supported by your host compiler. Again, if you're all working under Linux and basically under GCC as the host compiler, it doesn't make a huge difference. Now there's CUDA GDB. I'm personally not a GDB user, so I'm probably not in a great position to go into many details here. But basically the way that you do it is you have to instrument your code first. Well, you have to compile it with debug symbols turned on. And you have to turn the debug symbols on for both the host and the GPU code. So that's why you need to